Welcome, my dear students. We are in the third lecture of week 6. In the last lecture, we categorically most of those promising technologies and few we explained in few of them we explained in detail, whether it is related to your incineration, whether it is related to your pyrolysis as well as gasification. And at the last we also talk about that hydrothermal intervention. And in most of the cases, what was our observation? That definitely the output, the yield, whether it is with reference to your bio-oil or whether it is with reference to biogas or whether it is with reference to biochar or maybe hydrochar, it is basically dependent on the waste composition and what we wanted to achieve, means what is the output, what is that particular output we are looking for. So, based on that definitely we need to maximize our conditions in a way so that we can get the maximum output. And in that particular process we need optimization as well, because once we are handling with diverse waste material, optimization is a very key important issue, because if it is a segregated or a single type of waste, definitely the issue will not be there. So, in today's class we are going to talk about more of anaerobic digestion as well as fermentation for producing your energy. So, as we mentioned that this is going to be in this particular week, we are going to cover mostly those waste to energy interventions and those particular what are those possible options and technologies, as well as we will be also talking about your plastic waste and plastic waste, how plastic waste best can be managed through these sort of technological interventions. We will also like to see through these. So, the first thing which I initially mentioned, that anaerobic digestion, and basically this is a very important energy technology that breaks down organic waste and organic waste into your biogas, mostly your 50 to 70% of that is your methane, and organic fertilizer, and supporting a circular economy and reducing your greenhouse gas emissions. So, it is going to support in 3 ways. It is going to give you your biogas, it is going to give you some sort of digested, which is basically which can be used as a fertilizer like material, as well as it is going to capable to reduce your greenhouse gas emission. So, this biogas can be used for electricity, heat and biofuel production and contributing to your sustainable energy generation. And types of anaerobic this digestion and waste resources or waste sources. So, we have 2, one is your wet this anaerobic digestion, another is your dry anaerobic digestion. Wet anaerobic digestion is going to cover up with those particular material where you are going to get at least water or moisture percent more than 80%. That means mostly it is going to be useful particularly for your maybe your livestock, maybe your manure, maybe your sewage sludge, industrial and agriculture waste, which is basically dominance of your organic waste. And once you have that sort of waste, definitely you will be able to achieve that sort of conversion more efficiently. So, these will come under your wet anaerobic digestion. The other part is dry anaerobic digestion, where you can expect 20 to 40% of your solid content. And this is basically suitable particularly for your municipal solid waste, food waste, as well as lignocellulosic waste, means where you have a higher lignin content, lignin based material waste resources. So, what are the factors which basically impact this anaerobic digestion efficiency? The first thing is very important is your feedstock composition. If it is having a higher biodegradable content, definitely it is going to improve your biogas yield. So, that means the profile of that particular waste is going to be very important issue. Co-digestion, mixing complementary substrate enhances your nutrient balance as well as your microbial activity, because which is very important for that particular mediation, because this is going to be a microbially mediated process under your anaerobic system. So, definitely it is going to be influenced by that as well. Temperature and pH. Once it is going to be mediated by microbes, whether you talk about those thermophilic range or mesophilic range, we need to make sure that the optimal condition which is we are going to provide is ensuring your maximum methane production. So if you have that sort of condition, or if you have that sort of temperature or pH which we can make a stability over there, definitely we will be able to produce more methane. Pre-treatment methods like grinding means efficiency of this particular anaerobic digestion is going to be always based on that particular particle size, and if it is particle size, definitely it has to be grinded. And then steam explosion and acid hydrolysis definitely improve the digestibility and biogas yield by 20 to 30%. So this is a schematic representation that how this anaerobic digestion is going to take place, and what are those definitive waste resources, whether you talk about manure, whether you talk about those waste water biosolids, whether you talk about those food waste and other waste material, energy crops as I was mentioning, whether it is fats, oils, grease, crop residue, and particularly winery or brewery waste which is coming up. So these basically these feedstocks, as I mentioned, that these feedstocks is having definitive composition and varied composition. So this is if it is going to be digested singularly or in combination, that means co-digestion is also possible for better efficiency, for improving your more biogas yield. And once we go ahead with that sort of anaerobic digestion, definitely we'll be able to produce much of your biogas. And at the same time, in the output sector, we will have also your digested, and this digested is basically, as I from the very initial classes I was giving emphasis that these digested is just like a fertilizer material which can be used and which is enriched with your macronutrients, micronutrients and secondary nutrients, and also can be used as a soil conditioner. So, and if you look at this biogas, definitely whether you talk about electricity, whether you talk about heat, your vehicle fuel, renewable natural gas, and this can be, it's a wider horizon of use. And at the same time, when we talk about this digested, I mentioned very specifically that this can be treated as an organic fertilizer, or even some of the cases people also used as a bedding material, particularly for animal, and other products, particularly you can see over here that this building material, this digested can be used as a building material, as well as it can be used as a crop irrigation. So these are those definitive the strategies through which this material can be used. So these anaerobic digestion for different waste, particularly whenever we talk about these waste to energy conversions, definitely I said that multiple sorts of waste materials are possible that we can digest, we can follow up that sort of digestion process, whether you talk about municipal solid waste, food and green waste, which is going to contribute around 32 to 56% of the total waste globally, requiring your improved hydrolysis for your efficiency. So if you have it, definitely we need to make that sort of pre-treatment for making more efficient production of your biogas. The second thing is livestock manure. So there are challenges, and challenges include low carbon nitrogen ratio and poor degradability, requiring innovative pre-treatments are needed, particularly for improvement in that. Particularly once we are talking about that degradation, definitely we have to have it in a very faster or very speed up way. Sewage sludge, wastewater treatment plants are major biogas producer, converting most of your 50% of your organic matter into your energy. And if it is capable to produce that, but at the same time we have issues related to the sewage and sludge, because it may contain some of your heavy metals and metalloids as well, and which can make this contamination more pronounced way. The fourth component is your lignocellulosic waste material. Basically, once we talk about these which requires physical and chemical pre-treatments, because as it is containing more resistant part of that particular material, definitely it needs some sort of pre-treatment to improve its biodegradability and methane yield. Then food waste is coming up these days with much more areas, and particularly, and it's a widely prevalent cases we used to get this sort of waste material. This is highly biodegradable but prone to acidification. So that means it again requires some sort of process adjustment for your optimal methane production. And then we have your industrial wastewater. Traditionally, it is being processed, and if it is having a chemical oxygen demand more than 3000 milligram per liter, but your newer digest can handle lower COD waste effectively. So this is also going to be taken care of. And microalgae, and these particular, they have a huge potential, particularly for biogas, but require cell wall disruption for efficient digestion. That means whenever we talk about this diversified waste, definitely it all warrants some sort of pre-treatment strategies to make it more efficient for conversion of all of them to your biogases. So outputs of these anaerobic digestion basically generates two key products. I already mentioned about that, whether you talk about biogas and then digested. And biogas, I primarily mentioned that mostly it is dominated by your methane, almost 50 to 75% is there, your methane is there, and along with you have a carbon dioxide, and then hydrogen sulfide is also there, and you have as an admixture you may have a water vapor and trace gases, right. So this can be utilized particularly for your heat generation, electricity production and cooling applications. And purified biogas, known as basically renewable natural gas, is obtained by these removing carbon dioxide, water and hydrogen sulfide, because they don't have that sort of calorific value for giving more energy yield. So definitely we need to separate these impurities, and then only we can have that. So RNG can be injected into your natural gas grid and compressed for use as a vehicle fuel. Further, it can be processed to your produce alternative fuel, bioenergy products and biochemicals. And the other segment is this digest. This digest, the residual material remaining after your anaerobic digestion, definitely containing consisting your solid as well as liquid fractions. Liquid fractions always can be used in irrigation purposes also. It can be injected with that particular irrigation water, right. And this liquid digest, as I was mentioning, that these are very rich in macro, micro and some of your secondary nutrients, and this can be commonly used as an organic fertilizer, liquid fertilizer. And this solid digest used for multiple application, particularly in case of your, as I said, animal bedding, right, soil amendment and composting, raw material for bioplastics and bio-based products. And this digested utilization reduces mostly your waste, enhances your sustainability component and provides additional revenue streams for your biogas projects. That means if we look at that particular reduce, reuse and recycle, and that circular, the concept of circular economy, definitely it is going to be a win-win situation. Always we can go ahead. And what are the future trends and how these particular waste to energy, this intervention of your anaerobic digestion is going away. So there are integration with other waste to energy innovations or technologies, whether you talk about those particular gasification. I mentioned about that hydrothermal processing in your last class to maximize your energy recovery. So definitely we can make that sort of this process can be integrated with the other possible options which are available with us, and then we need to standardize and we need to make that sort of policy support for biogas utilization and commercialization and economic feasibility, research on additional revenue streams, particularly your bio-based chemicals to improve your profitability. That needs to be done on a continuous basis, and if we are able to do it, definitely we will be able to get that maximum output of biogas as well as those bio slurry or that digest, which can be used sustainably, particularly for agricultural point of view. The next technology is fermentation, and fermentation again, this is also something which is microbially mediated, microbial process for breaking down your organic waste and producing biofuels like hydrogen, bioethanol and organic acids. And unlike anaerobic digestion, fermentation can occur with or without oxygen. In the last case we have seen that this has to be done without your oxygen, but this can be done both with or without oxygen. And hydrogen production through microbial fermentation has gained interest in the present context due to its potential for clean energy production. This is gaining that popularity. And so what are the different types of your fermentation for this particularly waste to energy intervention? You have your dark fermentation and you have your photo fermentation. So what is basically dark fermentation? Dark fermentation is basically, this is an anaerobic process using, we are going to, as I said, this is going to be a microbial mediated, so bacteria is going to be used, and this bacteria is capable to convert waste into your biohydrogen, organic acids and alcohol. And these hyperthermophilic bacteria like Thermotogaceae improve the efficiency by operating at high temperature, reducing the contamination. So these hyperthermophilic bacteria is capable to do that conversion, right, and reducing, at the same time it can reduce your contamination. And in photofermentation, which basically uses your photosynthetic bacteria, which can convert your organic matter into biohydrogen under sunlight and anaerobic condition, right, and it can be integrated with dark fermentation to improve your hydrogen yield. So one can make that sort of integration with that sort of dark fermentation to get more of your hydrogen. So what are the challenges? The most important challenge is you have a low hydrogen yield to the tune of only 4 to 5%, particularly this limits basically large scale adoption or maybe scaling up of this particular technology. So what are the emerging technologies to enhance this efficiency? We have microbial electrolysis, which basically reduces your carbon dioxide emissions while increasing your biofuel yield. We have your synthetic biology can be used, genetically engineered microbes enhance these waste conversions. But there are some ethical issues are always there with these genetically engineered microbes. So we need to be very cautious once we are going to use it. Solid state fermentation, I already mentioned in your last week class about how it works. So this basically uses solid waste feedstock to improve your efficiency, particularly your agricultural residue. And you have, at the same time, you have your membrane bioreactor. And this membrane bioreactor can, improve your microorganism retention, reducing downstream processing cost as well. So in all this process, particularly once we are talking about those emerging technologies which has been evolved in the last few decades, so there must be some pre-treatment and co-fermentation is must. So what is that? Basically this is a mechanical, thermal, chemical and biological pre-treatments which actually enhance the waste digestibility. And once I am talking about co-fermentation, this basically balance your nutrient CN ratio. We have seen it with some particular nutrients, particularly from animal residues. Those animal residues, definitely you may have that sort of low CN ratio. So it is going to, it can balance that CN ratio, improving volatile fatty acid production and biohydrogen output. So what are the future directions? Means, in what way we are coping up with this particular technology, and in what way we are trying to make that sort of refinement or innovations. Industrial scale continuous co-fermentation instead of batch processes. So mostly as of now, mostly batch processes are mostly common, but people are trying to coming up with your industrial scale which is going to do it on continuous mode. Integration with other waste to your technologies like your anaerobic digestion, like your pyrolysis for better energy recovery. And policy support and economic viability is always going to be there to scale up this particular fermentation based biofuel production. So, and the last one, which is basically related to your chemical conversion. We talked about, in this particular class, we specifically mentioned about definitive technologies related to your anaerobic digestion. We talked about fermentation, and this is going to be related to your chemical conversion. And what does it mean? This chemical conversion basically transforms your waste oils into your biofuels, whether you talk about this biodiesel or renewable diesel via this trans-esterification and hydrogenation. So these are the two mechanisms or mediations. Either it is going to be your trans-esterification or it is going to be your this hydrogenation, which is going to be very, very important. And these methods basically supports your decarbonization and waste valorization. And once you have a dependence on it, definitely it is reducing dependence on your fossil fuel. So what are the key chemical conversion process, particularly in this your chemical conversion? The first one, as I said, trans-esterification, which basically converts your waste oil, fats and lipids into biodiesel and glycerol using catalysis or catalyst. Definitely it is going to be a catalysis which is going to be enforced over here. That means you need some catalyst as well as alcohol, either maybe methanol or ethanol. And catalyst can be homogeneous, either it is acid base or heterogeneous like your reusable solid catalyst, or enzymatic means your green synthesis. And recent advancement focuses on using these nano catalyst and low cost waste based catalyst as well. Means there are few developments particularly in the field of your catalyst where people are using eggshells, chicken bones and anthills, which are basically nano catalyst, which is having a more this conversion efficiency. So this is basically that trans esterification process, where basically once you talk about that waste and then you have filtration and then moisture removal is carried out, and then we wanted to reduce that free fatty acids which is being generated, and then this trans esterification. And once I am talking about this trans esterification, definitely we are going to get your biodiesel, finally what we are looking for. And through these class, particularly in today's class, we wanted to understand that yes, the definitive modes, the three different modes of these waste to energy conversion technologies or technological options, whether you talk about this anaerobic digestion, whether you talk about fermentation, and the last one, when we talk about that particular with reference to this chemical conversion, we have a detailed outlook of how these different technologies, although they have in many cases they have few your disadvantages or limitations, but definitely they are going to be always we need to be very careful about that particular composition of waste is very important, I initially mentioned, and the output for which we are looking for, that has to be taken care of as well. And based on that, this particular energy transformation process has to be operated, and based on that we need to look into those definitive or greater details with those the mechanisms as well as the possible options, because if we wanted to have that sort of maximization and optimization of those resources, because once you are going to handle with diverse material with diverse composition, definitely those those maximization and optimization of those resources as well as the available conditions need to be optimized. So thank you very much. We'll look into the other parts of this waste to energy material in the next class. Thank you.